This webcast is the first in a series designed to provide a strong foundation for RF engineers learning LTE technology. Joining us to present today is Frank Palmer. Frank joined HP Agilent in 1986 as a product marketing engineer for portable spectrum analyzers. He's held positions as wireless industry marketing manager and wireless applications engineer, where he was responsible for understanding the test requirements of the diverse wireless communications industry. He has authored and delivered various technical papers at industry symposia and seminars, including numerous LTE training classes. Frank is currently a worldwide wireless and LTE industry lead. We'll begin today's webcast in just a moment, but first a little bit about the process. Frank will answer questions at the end of his presentation today. To participate in the Q&A session, you can enter questions at any time during this presentation in the question window on the lower right-hand side. Be sure to address your questions directly to all panelists by clicking on the pull-down menu. We have a lot of people online with us today, so I apologize in advance if we don't get to all of your questions. But don't worry, if we run out of time, we will respond to the remaining questions via email. We also ask that you take a moment to fill out the short feedback form that will appear when you close the WebEx session. Now let's move on to the presentation. Welcome, Frank. You now have the floor.
All right. Well, let me get there. Thank you, Allison. So again, everyone, welcome to part one here of this webcast that's based in part on the second edition of Agilent's LTE book. This is the agenda. We'll first spend a few minutes discussing why and what LTE is, and then this is followed by a fundamental discussion on the RF aspects of the air interface. And then we'll go about and talk about some of the approaches towards testing transmitters and receivers before ending with time for question and answers. There also is a part two, separate follow-on webcast, and that's going to cover MIMO concepts, and it's more focused on LTE Advanced, his features and design challenges. So let's get started with LTE and what's driving it. Well, we're always looking forward to modifying the existing technologies or creating new ones in order to improve the data rate. The data rate is one, having higher data rates is something that's really driving these systems. In addition, operators are looking for backwards compatibility. And then obviously, they all want lower complexity, and they want to continue on with cost reduction, reducing their capital expenditures. And the all IP core packet switch system helps in part to support those goals. And some of the significant requirements for LTE are the higher mobility with access across the network at up to 350 kilometers per hour, improved latency, which is down from 150 milliseconds for UMTS down to 10 milliseconds, and because of the effect that it has on the user's experience, particularly in some of the voice applications like voice IP and other latent sensitive applications like gaming. And then there are required spectral efficiency numbers, hoping to get something like 3 times improvement over what HSDPA was. Now, before I can get to some of the details on LTE, I just want to take a moment here to let you see and talk about where the standards come from. The International Telecommunications Union, or the ITU is what it's called. It's a United Nations agency for information and communication technologies. And it has 3 major activities: standardization, development, and radio communications. It plays a key role in the global management of the RF spectrum, and it ended up developing the IMT framework of standards. And here I'm showing on the left the IMT 2000 and the IMT Advanced standards. There's international or the regional standard bodies such as ARB in Japan or ETSI in Europe. What they've done is they individually and more recently collaboratively as the 3GPP submitted proposals for these standards, with the LTE Advanced proposal being the one that's submitted to meet the IMT Advanced, which is also known as the true 4G. And you may notice down here that the highest data rate listed is 1 gigabits per second for this IMT advanced standard, and LTE itself doesn't meet that. That's the number for LTE advanced. So how does LTE fit in? Well, looking at this timeline of 3GPP releases, the LTE is just, as that name implies, it's really an evolution of technologies. UMTS actually started back in 2000 with release 99 for WCDMA, and then it's kind of continued on through release 7, where LTE was first discussed as a study item. And then in December of 2008 with release 8, it was actually fixed as the first standard. And then there's the follow-on enhancements that then go to further define LTE or evolve it into LTE advanced. So let's take a look at some of the key technical features, and as we're talking about some of these, maybe you want to keep in mind some of those motivation and goals that we discussed earlier. So access mode. LTE uses both frequency division duplex and time division duplex. For FTD, the uplink and the downlink have dedicated frequency bands, and for TDD, the uplink and downlink share the frequency band over time. And we also refer to these as using paired and unpaired spectrum. The majority of systems that have been deployed already use FTD, but TDD is looking to grow, particularly as China Mobile rolls out its systems later this year. Channel bandwidth. LTE has flexible channel bandwidth from 1.4 megahertz up to 20 megahertz, with the wider 10, 15, and 20 megahertz really targeted for new spectrum use and the much higher data rates. The transmission schemes, there's two different for the uplink and downlink, OFDMA and SC-FDMA, and we'll talk about this more in detail in a few minutes. Modulation formats, well, there's really a selection of now higher order-based modulation formats, and those can be selected based on the specific radio channel conditions. MIMO technology, I'll just say that it's a multiple antenna technique which is used to improve the data capacity, and we're going to discuss that more in detail in part 2 of the webcast. The peak data rates, LTE aims to have up to 300 megabits per second peak data rate, and that's with a 64 QAM modulation and a 4 layers or 4x4 MIMO, and obviously the widest channel bandwidth. And I might add that that is under ideal conditions. And for the uplink, it's a 75 megabits per second peak data rate. Under bearer services, LTE uses a packet switch only, so it's going to end up having to use voice over IP for voice communications with some guaranteed bit rate. And this requires priority handling or some level of quality of service implementation. And then there's the transmission time interval, or TTI. The TTI is the time it takes to transmit one block of data, and this has been significantly reduced from the previous systems. And one of the significance of that is that it's really a key part of the smallest time or the smallest interval over which the channel conditions can be reported and thus adjusted. So let's now move to discuss some of the air interface concepts, starting with the frequency bands. This table here shows the frequency bands for FDD. It's inherited actually all of the existing UMTS bands back in from 2008 when the specs were actually fixed, and then some additional new ones have been added since. If you look at the frequencies there, you can see that there's an overlap or subsets of frequencies, and that means that for many of the existing power amplifiers and receivers that the RF coverage in those areas may not be an issue. But however, the narrower duplex spacing and the gaps that's going to make it hard to design filters that prevent the transmitter's spectral regrowth from leaking into the receivers. And also, it adds complexity to designing the multiple antennas. So in other words, it's about the ability to implement the multiple bands in the devices is where that can cause some issues. Here are the TDD bands. For TDD, there's no concept of duplex spacing or gaps, since the downlink and the uplink frequencies are the same, so they're transmitted on the same band. And so the challenge there of separating the transmit from the receive doesn't end up falling on the duplex filter that's used in the frequency domain, but rather it's a switch that's used for the time domain. The OFDM enables flexible transmission bandwidth. The transmission bandwidth is determined independently by the number of active subcarriers or RBs or resource blocks. And this gives the LTE the flexibility to have 6 different configurations that range from 1.4 megahertz up to 20 megahertz. The channel bandwidth here is defined in megahertz. It's the nominal occupied channel, or also known as the channel spacing. The transmission bandwidth configuration is defined in units of RB, and it's the maximum number of RBs that you can have for a given channel bandwidth. And then we have the transmission bandwidth, and it's also defined in RBs, and it's the number of RBs that are allocated to any specific transmission. And that number can vary anywhere from 1 all the way to the actual transmission bandwidth configuration. So OFDM, or orthogonal frequency division multiplexing. What that is, it's a multi-carrier modulation or transmission scheme that divides the carrier frequency into a large number of closely spaced orthogonal subcarriers. The multi-carrier scheme achieves these transmission efficiencies, which end up being similar to some of the traditional single carrier schemes, but it ends up doing this with better immunity to some of the common channel impairments. And it can do this by using a proportionately slower symbol rate as compared to the single carrier schemes. Now the scheme is robust, ends up being robust in the presence of single frequency interferers and some of the noise, but because it's very robust in that sense, because if you end up losing a carrier, or if you end up losing a couple of carriers, it's not completely fatal to the entire transmission. Typically, these lost bits can be recovered through many of the error correction algorithms. So if we're looking at the single carrier, or the single subcarrier, the rate of change of the phase modulation determines the position of the zero crossings. And so if we can think of the subcarrier modulation rate, if we can link the subcarrier modulation rate to the subcarrier frequency spacing in a way that the nulls of the spectrum of one of the subcarriers can line up with the peaks in the adjacent subcarriers, we can end up getting orthogonality for the subcarriers. And then we can end up with a spectrum similar to this. And so what it does is it ends up operating as an orthogonal narrowband system. And the spacing creates the orthogonality. And then we have phase noise along with frequency and timing assets that end up working against that orthogonality. Now, we can remember that if we look at this, you can see that each of these assigned carriers has a modulation symbol that ends up modifying its magnitude and phase. And these here are all shown at constant amplitude. And obviously we know that's not the case. We have non-constant amplitude modulations such as the 16 or 64 QAM, and those can be used. We talked about that with respect to changing those modulation based on link conditions. Now, the number of subcarriers that are assigned to each user can vary depending on the data rate. And so as the data is spread out over this number of subcarriers, it's less susceptible to single frequency interference and multipath dropouts. LTE itself, it ends up using a form of OFDM called OFDMA, which is orthogonal frequency division multiple access, which is more flexible, and it allows subcarriers to be allocated to different users in time and frequency. And this provides really a much needed frequency diversity for these low data rate cases, which are narrow frequency allocations that end up being susceptible to narrowband fading. Typically, the channel pattern per user will frequency hop after each symbol or every few symbols, and this hopping is one way to provide better immunity to the fading versus the static assignments. So there's several advantages to OFDM, including its scalability in the frequency domain and its support of frequency selective scheduling within the channel. There's wide channels that can be created which allow for high data rates when, of course, that's when the spectrum is available. And then there's the long symbols in OFDM. What it does is it allows symbol extension using a cyclic prefix in order to completely avoid multipath distortion. And it does this with the insertion of a guard period or a guard interval, and they insert that in between each symbol, and that eliminates all of the inter-symbol interference so long as the length of that period is longer than the multipath delay spread in the radio channel. And unfortunately, of course, though, with things there's some disadvantages too. The close subcarriers are susceptible to frequency errors and phase noise, which end up creating inter-carrier interference. And there's double-sided Doppler shift that's caused by signals coming from, at the same time, coming from the front and the back due to reflections. And that's particularly hard to deal with and can require a large amount of DSP computation in order to address. And then, of course, we'll also see in a little bit here the subcarriers in OFDM signals. They combine to create high peak-to-average ratios in the time domain, and this creates compression and spectral regrowth problems for amplifiers that can be expensive and kind of timely to deal with. Single carrier frequency division multiple access, that's a new concept in the transmission, and it's used in the uplink for data transmissions only. And this diagram here shows that approach. Now, SC-FDMA is what we call a hybrid transmission scheme. It's one that really tries to combine the best characteristics of single carrier systems, like the low peak-to-average ratio, and tries to combine that with some of the frequency domain flexibility and the multipath resistance that we have in OFDMA. So let's try to compare the two, and we can start off doing that by taking a physical view of how the OFDMA and SC-FDMA look in the time and frequency domains. And we're going to do that by taking a look at the transmission of this series of 8 QPSK symbols. Now, on the left, I have the OFDMA, which is really the simpler of the two schemes. It has a one-to-one relationship between the modulating data and the subcarriers. And now, since this is just a 4 subcarrier example here, we've got the 4 data symbols that are here. They're all going to be transmitted in parallel, and they each end up occupying 15 kilohertz of bandwidth. And so for those 4, that total is 60 kilohertz. And then after these first 4 symbols are transmitted, then what we do is we take the next 4 as a group. Now, for SC-FDMA, the process that we go through looks actually very different. Excuse me. Each of these modulating data symbols occupies the full 60 kilohertz bandwidth, and they end up being transmitted sequentially which is more like a single carrier type of scheme. So let's take a look now at how these schemes go about actually generating the signals. And we'll start with the OFDMA. So here in this example, I have 4 subcarriers down here. You can see that they're all spaced 15 kilohertz apart, and each one is shifted by the QPSK symbol. So you can see the different phase relationships there. Now this final waveform here is just simply a summation of these subcarriers. Now the randomness of that final waveform here actually will increase as we increase the number of subcarriers, and in the limit, this composite waveform ends up resembling Gaussian noise. And if we know, Gaussian noise has the Gaussian noise distribution has a very high peak to average ratio. Well, for SC-FDMA, the signal generation process really starts by creating time domain waveforms. So here's our QPSK symbols that we're going to go through these points, and they all go through in one SC-FDMA symbol, and that symbol length is the same for OFDMA in this example as well. So we start by creating the time domain signals, and then these time domain signals are converted to frequency by a discrete Fourier transform, and it's created such that they can be represented by these four bins that are spaced at 15 kilohertz apart. And then what we end up doing is we shift these to the correct place in the channel bandwidth that we want, and we end up then taking this frequency shifted signal and converting it back to the time domain with the inverse FFT. But the real crucial characteristic really is this process is that the peak to average ratio of this final frequency shifted signal ends up being the same as that of the original modulating data. In this case, that was QPSK, and this is very different from the OFDMA case that we had for the same occupied bandwidth and the same data rates. So here we can compare the two schemes by looking at the CCDF curves, or complementary cumulative distribution function curve. And what this curve does is it shows the probability as a percentage, which is on the y-axis. So it's the probability as a percentage, or what I like to say, it's the amount of time that a signal will end up reaching some given level and be at that level or greater above the average power level, which is referenced here at 0 dB. So looking here, we can see that the single carrier FDMA curve has clearly lower peak to average ratios than the OFDMA, and there's several dB of extra headroom that in comparison could end up resulting in a lower cost power amplifier because of the less spectral regrowth. Or perhaps there may be no or some less costly linearization techniques that may be required, which ends up lowering the power consumption and resulting in better power, better battery performance. The frame structure here defines the frame, the slot, the symbol structure, all in the time domain. And there's two structures. There's a type 1 for FDD and type 2 for TDD. Now, in each radio frame, it's 10 milliseconds, and that 10 milliseconds consists of 10 subframes here that are each 1 millisecond. And each of these subframes consists of 2 slots of half a millisecond. And so there's a total of 20 slots in the frame. And this is the same for FDD and TDD. Now, in FDD, the uplink and the downlink have the same frame structure, but they end up using different spectrum. Whereas in TDD, we have to switch in time between the uplink and downlink. And so a flexible assignment for the uplink and the downlink utilizing a special subframe is what allows for the change in direction within a frame, and it also allows to make it better able to handle asymmetric data rates. So now let's look at the slot structure, or what's also called a resource grid, and this is very similar for the uplink and the downlink. First we have here a resource element. The resource element is the smallest unit in the physical layer, and it occupies one symbol in the time domain and one subcarrier in the frequency domain. Now, the resource elements are used to make up what's called a resource block. The resource block is the basic unit of scheduling. It has one slot, which is a half a millisecond in the time domain and 180 kilohertz in the frequency domain. And the numbers of subcarriers and the symbols in these change depending on the cyclic prefix and the carrier spacing. So for a normal cyclic prefix, there's 7 symbols and 12 carriers, which end up being 84 resource elements. The LTE frame has physical signals and channels, so let me just give you a brief description of some of these for the downlink and uplink. There are synchronization signals for the downlink. These are all used by they're used by all the UEs for timing and center frequency, as well as this process called cell identification. If you're familiar with the UMTS process, it's similar with the scrambling codes and finding the code groups. There are reference signals, and there's 3 types. There's the cell-specific is the most common, and they're used for the downlink channel estimation. And another characteristic is that they have a known amplitude and phase. And I'll talk about that in a bit about how we use that information for testing as well. There are the shared channels, and those shared channels carry the data traffic, and they're shared in time with multiple users, and they can be QPSK, 16, and 64 QAM. Then there are the broadcast channels, and that carries cell-specific identification content, and they're modulated at QPSK. Then the control channels, they carry out allocation and control information, such as the transmission bandwidth configuration that we talked about in the channel bandwidth section. And then there are some indicator channels. The HARQ indicator channel, it carries the acknowledgments and negative acknowledgments feedback that's used by the UEs for to communicate that the uplink blocks have been received by the eNode B. And then in the uplink, again, reference channels used for synchronization and channel estimation and this link adaptation. There are shared channels. Again, just like in the downlink, it carries the traffic data and can be QPSK, 16, or 64 QAM. Control channels, again, carries control information such as the scheduling requests, and in this case, the HARQ ACKs and negative ACKs. And then there's the random access channel, and what that channel does is initiates communication with the eNode B and carries preamble information and allows the eNode B to calculate the time domain, time delay to the UE and also identify that. So here we see the frame structure of the downlink. We have it color-coded here with different physical signals and channels just so you can see how they can be mapped in. So let's just take a look at just a few of those. So for the reference signals or the pilot signals, we can see that they're transmitted here in the first and the fifth OFDM symbols. The primary synchronization signal is kind of purple or lavender color here. It's ended up being mapped to the last symbol of time slot 0 and time slot 10. So if you look further down, you can see it here as well out of the zoomed in part. And then a broadcast channel, one more here. You can see that's ended up mapping to the first 4 symbols that are in time slot 1. And both of those, the synchronization channel and the broadcast channel, you can see are in a centered 6 RB section. Now another way to look at it here is also frequency and time view of central 144 subcarriers that are in the downlink. And here you may notice the control channels here in green. They exist on all the subcarriers, and it does so at the start of the first slot. And you can also see in there the reference signals, which are these blue ones, how they end up showing every 6 subcarriers on the first symbol 0 position, as well as symbol 4. So they end up repeating as you go out in time. Now, if you look in the center here, you can see a narrow allocation of the synchronization signal and the broadcast signal or channel. You can see that's pretty clear in there. And this narrow allocation is done in order to make the frame structure completely independent of the chosen system bandwidth. And we know that that bandwidth can vary from 1.4 to 20 megahertz, and so we don't want it to have the bandwidth to have to affect that structure. And then we have the modulation depths that are applied to each symbol. Those would vary according to the channel type. So let's move on to transmitter, receiver, and test fundamentals. We talked about some of the key area interface concepts. Let's talk a little bit about testing. So here I have a basic functional building block of a digital communications transmitter. This basic block here I'm showing, it applies to LTE, though there's probably more levels of integration that would be in an actual LTE transmitter. There's possibly be some sort of transceiver maybe, or there could be a second transmit band, there'd be additional antennas, and maybe between the RF and the baseband some sort of digital interface. But in general, the process that the transmitter goes through, is how it's here outlined on the left. So we start with channel coding, where there's error correction, interleaving, some processing, which is putting it into the frame structure. And then that's followed by some symbol encoding, where we map the serial input stream into I and Q baseband signals. And then there's a modulation filter. In many of the previous standards, there was that would be a Nyquist filter. And what we use that for is to ensure that we have accurate data transmissions. And then that'll be followed by modulation, where we use mixers to upconvert the baseband signal to the IF or the RF frequencies. And then amplification and filter. We do that with the output to limit the potential interference that the transmitter might have with other transmitters in the areas. And then, of course, gain control, where we're able to set the specific power level or adjust the power level of the transmitted signal. Now, the RF analysis is done out here at the antenna, and that's used really to evaluate the complete transmission system. And the 3GPP has put together specified characteristics tests to do that. And I've grouped those characteristics tests just in these kind of 3 general categories. And they are the output power, transmitted signal quality or modulation quality, and unwanted transmissions. Here they're further described by the names of some of the specific tests, probably some that you may be familiar with, such as channel power, the EVM, adjacent channel leakage ratio, spectrum emission mass. And also for your reference here, what I've done is I've included the 3GPP technical specs documents and chapter numbers for the conformance test. That includes the specifications for that test as well as the test procedure. So those tests that we've just shown are used to evaluate, again, the complete transmission system, but RF analysis is also used in order to evaluate subsystems and their components. And what that would mean is it's going to require probing at different parts or different locations within the transmitter. And in here, what I'm trying to do is show you how you can end up using the same type of RF analysis software at different points in the transmitter chain. And so, for example, we could use this vector signal analysis software along with this logic analyzer here to maybe try to understand the quality and the content of the digital data that would be right here input to this DAC. And And then what we do is we take that and compare it to what's at the analog output of that DAC. Now, with higher levels of integration and increased DSP, techniques such as crest factor reduction and predistortion in the baseband of the transmitter adds complexity to the understanding of the RF measurement results. And that's whether it involves a spectrum or time domain type of measurement or a digital demodulation analysis. So for the evaluation of components and subsystems, what we want is an incremental and structured approach where what we can do is in the system stimulate it with, say, for example, a signal generator like I've shown here, and then make successive measurements at these other points in order to quantify the contribution of the amount of distortion or spurious and other impairments. So this systematic and structured approach to verifying the transmitter performance is really set up to follow this verification sequence, and that verification sequence begins with basic spectrum measurements and then continues with vector measurements before you end up switching to the modulation analysis. And typically it's much more productive and probably more efficient to go about doing it in these steps, even though many times it's pretty tempting just to go directly to the advanced digital modulation. And really we want to do that process because it actually improves our chance of perhaps finding some of the underlying signal problems and identifying those earlier before they end up being masked when we try to make measurements on the complex signals. So in doing some of that verification, channel power, amplitude flatness, center frequency, occupied bandwidth, those are all spectrum measurements that can be made on the LTE signal. With the center frequency and amplitude flatness are more indicative since the official definition actually requires digital demodulation. For channel power, that can be measured by averaging the spectrum or by doing RF envelope measurements with band power markers, and most signal analyzers have these band power markers already. For power versus time measurements, those are pretty much very much interest in LTE due to its varying signal structure of signals that it has. You know, there's different reference signal locations, channel locations, and such. And initially, when you're doing these can be made without demodulating the signal, and we do that in order just to verify some of the absolute power levels. For CCDF behavior, that also can be measured. In particular, we might want to do that using time gating with the vector signal analyzer. And what that can do is it can provide some quantitative measurements of the signal power's behavior that can be very useful in evaluating the different operating points and efficiencies of transmitters. So with that, let's take a look at the results of two measurement examples for occupied bandwidth and then spectrum versus time. So for occupied bandwidth, what I have here is a fully allocated 5 megahertz downlink signal for this measurement. Down here, we can see we're reading the occupied bandwidth is 4.47 megahertz. And from this measurement, the occupied bandwidth measurement here, what I can do is I can also calculate what the center frequency is from the centroid of the occupied bandwidth markers, but that's with an assumption that the allocation that we've done is symmetrical. And then also looking at the trace, we can get an accurate power measurement. Because it makes an accurate power measurement, we can get an idea of what the amplitude flatness would be from viewing the trace here and making measurements. The spectrum versus time, or the spectrograph, this is really one of the most useful general or non-demodulation measurements for LTE. The y-axis is time from top to bottom, with the x-axis being frequency, and the power level, of course, is then denoted by the various color. And what it does is it allows us to just have an overall view of the signal at a glance and interpret some of the different characteristics. We can see some of the major signal characteristics like the channel types here. We can see there's some shared channels, and you also can see symbol transitions, and it's really useful for complex signals like such as this in the downlink. And this is very similar to that frequency versus time view that we were looking at when we were looking at the channel structure. Another example here you can easily see is that the control channel here, that there's 3 symbols of the control channel that show it's being fully occupied over the full bandwidth of the signal. So that was the spectrum and vector measurements. So now it's time to focus a little on the digital demodulation techniques. But before you can go about demodding, you have to know and you have to set some of the basic parameters. Previously, we have been, we've had the frequency, the bandwidth, and the input range. And so in this case, what we do for the demod is we'd have the center frequency, the input range, just as we did before, but then we'd want to also know about the direction, either uplink or downlink, and that's because the sync structure and the modulation for those two can be different. And then we would want a selection of duplex, whether it's FDD or TDD. And then the channel bandwidth and the sync type as well. And then selecting the various sync types in there, just doing that selection itself can serve as a form of verification. Whether we have a good sync or whether it can sync well or not is just a simple level of verification test that can happen. So if we set those parameters, we can do a demodulation on the LTE signal, and we can end up getting traces or measurement views such as these. Modulation quality is really one of the most critical transmitter tests. It ends up measuring the amount of distortion in the transmission, and it usually affects the ability of the receiver to decode and process the signal with a minimum amount of errors. Now, in addition to the composite EVM, which is a required measurement by the standards, it's really desirable also to measure the EVM of the reference signal, and we want to do that separately from the data payload. And this requires some sophisticated demodulation and post-processing tools, and that's what I have here with this LTE analysis software on the 89600 vector signal analyzer. What it does is it can provide a number of different EVM metrics, including the composite signal that I mentioned is needed, measuring the data channels EVM separately, or the reference signals EVM. And then there's also some quick checks for frequency error and such things as the synchronization correlation. And that number should be close to 100, and that's really how good of a lock we are to that particular sync type that we've chosen for the uplink and downlink and the type of duplex. And then also there are some auto detection of the cyclic prefix and some cell ID information that's here. Now, in addition, in the frame summary here, we can see individual active channels and signals. We also get a look at the IQ constellation. And next to that, we have error vector spectrum, which is EVM versus carrier, and we have error vector time, which is EVM versus symbol. And then we also get a spectrum display. And from there, we can determine things such as occupied bandwidth. In this case, if we look at it, we can see it's about 4.5 megahertz, and that would represent a fully allocated signal. And then if we use band power markers in there, we can get a measure of the aggregate signal power. Now, as we're doing modulation analysis with the software, a real powerful capability of this is to use the coupling of markers. And this is really useful for LTE because LTE typically has a large number of symbols per frame or signal elements such as channels or reference signals or subcarriers. And what this coupling does is it allows us to understand and identify characteristics of a symbol in the time, frequency, power, and error all at the same time. So with the markers coupled and all of the signal and channels selected here, and we can do a peak search. And we do that in this error vector time mode. What that does is it ends up showing or putting a marker on the largest error in the subframe. And then for that tracee, if we look down here on the bottom, I've kind of highlighted or tried to redo this to make it a little clearer for you. But in the bottom we can see for that tracee marker that it's 64 clam modulation, it's the shared channel, and that's from symbol 11. And it ends up being located on carrier 150, which is on the outer edge. And then if we go back and look at the marker in the IQ constellation, we can also see that it's at a high power state, so very far from the origin. And then looking at the error vector spectrum, we can see that the error, so all of these markers represent the same position, that we can see this high error is consistent with what we would expect in the error vector spectrum that shows the highest errors at the cell edges. So now let's move and talk a little bit about the receiver. So in the same token as we did for the transmitter, the basic functional blocks here in the receiver, this works for LTE as well, and though there, again, is probably more levels of integration. There might be, again, a transceiver, there'd be perhaps a second receive channel, additional antennas, and probably some sort of digital interface between the RF and baseband. And the process that it goes through is pretty much just the reverse of the transmit. But the main objective of the receiver testing here is to make performance measurements on, again, on the complete receiver system. And in the same token, the 3GPP has put together some specified characteristics tests here that I've grouped into these three sections: sensitivity and dynamic range, susceptibility to interference, and unwanted transmissions. And similarly, what I've done is, given you the reference to the technical specifications docs that has the specs and a test procedure. But these characteristics here are performed in what we call open loop, and that is without feedback. And the 3GP specs, though, to have full or complete verification of the overall receiver performance requires closed loop testing with feedback through a faded channel. So in the receiver, there's many factors that can influence the performance, and so just like we had in the transmitter, it's useful to consider receiver subblocks and components in order to test for uncertainty contributions. So the front-end AGC or automatic gain control has to account for the downlink high peak-to-average ratios, which can be greater than 10 dB, and it has to do that so that the amplifiers can handle the peaks and not distort. In addition, when it's being used, the AGC, the phase changes that can occur because of the multiple gain stages can affect the demodulation signal quality, and that has to be tested as well. Receiver EVM, that can be used to give an indication of impairments such as non-ideal phase response, as well as IQ imbalance and compression. So let's take a look at a couple of measurement examples for amplitude flatness and linearity. What we want to do is we want to measure the channel and ensure that it's flat across all bandwidths. We know for LTE it has some very wide bandwidths, and so we want to ensure that it's flat at there, particularly on the band edges where for FDD we have duplex filters that can attenuate the edge of the signal. And also undue phase linearity errors or poor response can result in degraded EVM. Now, the receiver can do some of this correction in itself, but in order to do this, you're relying on the receiver to do this with the reference signal, and that can degrade the signal to interference plus noise ratio, or the SINR. And so the way the receiver front end can be tested for amplitude flatness and phase linearity is by stimulating it with an LTE signal and then demodulating it. And if you take a look at this, and it may be hard for you to kind of look at some of the display here, but for the flatness, the dB per division we're showing here is about 0.05 dBs, and so the range on this measurement here is about 0.15 dB, kind of peak to peak, and then for the phase, it's about 2 degrees peak to peak on here. So we just reviewed some of the RF front-end measurements. The baseband has measurement goals that I've stated here. And the question at hand is it possible to test the baseband independent of the RF section? So digitized signals are sent to the baseband where FPGAs and ASICs perform the demodulation, but now the receivers have to demodulate the signal and provide the results. Another challenge with testing the baseband section is how to physically deliver the test signals. Depending on where the receiver is in the development cycle, the test signals that you might want to use could be either RF, IF, analog IQ, or digital IQ. And further, for LTE, the digital IQ may be required to be an industry standard digital interface such as CPRI or DigRF. There are solutions available today for this, such as the Agilent RDX that's shown here for DigRF. Now, I mentioned that the receiver could be in various stages of the development cycle. Another solution to test this is to combine design software with test equipment to configure what I call an integrated design and test solution for RF mixed signal receiver hardware testing, quite a mouthful. Specifically, this example is for an LTE downlink open loop bit error rate throughput test. And so let me just kind of explain this in steps a little bit. What I have here is a system view, which is a design software package, and I have a workspace in here that creates a LTE signal, and it does that with known data traffic and then downloads the signal basically to the MXG signal generator, which ends up converting it and stimulating the receiver front end. Then the signal goes through to the device, and it ends up being captured here at the output of the ADC. And it's captured by the combination of the logic analyzer and a VSA vector signal analyzer software, which could reside either in the logic analyzer or over here in the PC itself. Now, the captured data is processed actually in system view in that workspace by a simulated LTE baseband receiver. The timing and the synchronization is handled within the system view, and it ends up calculating and reporting out the LTE bit error rate and the throughput. So you've seen a few examples of our test solutions, but our LTE portfolio actually provides design and testing, provides for the design and testing needs all the way across the entire life cycle. And we start with early design simulation and continue through development, integration, validation, and conformance and manufacturing. Our products end up being very complete and advanced because we're kind of at the forefront of these new technologies. We have technical experts that are very active members, and they end up providing leadership on over a dozen telecom standards and committees all around the world. And what this does is that allows us to have and to gain insight on where the industry is going and what challenges there are, and then we design measurement solutions into our products based on that information. One of the most prominent committees is the European Communication Standards Institute, and on that one we have several participants, including some that are working on the working groups that define the LTE conformance standards. In addition, we have tools that help you study these new technologies either through various technical content such as the LTE book, which is based on application notes for LTE and LTE Advanced, videos on our YouTube channels, as well as hosting symposiums and seminars like these. So with that, I'd like to turn it back to you, Allison, for questions and answers.
Okay, thank you, Frank. Before we start the Q&A session, I'd like to remind everyone about our survey today. Agilent holds many free webcasts throughout the year, and we ask that you take a couple of minutes to complete the feedback form that will appear when you close the WebEx session. This enables us to deliver the content that you need. All right, now on to the Q&A. If you have a question, simply enter it in the question window. Now, Frank, here's your first question.
Okay.
So you mentioned testing baseband independent of the RF. How can the baseband be verified?
Okay. Well, for FPGA verification, systems use LTE baseband library. We have a verification library that has a full baseband coding and decoding functionality for like CRC, turbo coding, rate matching. And that can be used to generate test vectors at various stages along the LTE coding or decoding chain. So say, for example, you're writing a HDL code for a scrambler block. You can take the input to system view's scrambler block to generate test vectors. And then what you would do is you'd input your HDL code, and then you'd compare the output vectors of your HDL code to the system view generated vectors. The nice thing about that is that it allows you to independently check your HDL code with a commercial test vector reference rather than writing your own. And then if you're doing FPGA hardware tests, you could use a dynamic probe to measure at intermediate stages within an FPGA implementation, say before and after FIR, and then using that probe along with the logic analyzer and VSA software like I showed, you can evaluate and debug the FPGA design and measure the impact that the FIR is having on EVM performance. Okay,
great, thank you. Second question, how have LTE deployments been going?
Okay, well that's one thing I didn't really talk about here much, but LTE in itself is it's been very well accepted. It's growing actually very fast. In fact, of the networks that have launched in the last year, of the total number of LTE networks that have been launched, just in the last year alone, 67% of all the new networks have been launched just in 2012. The GSA also estimates that by the end of 2013 that there's going to be approximately 230 or so deployments by the year end. So it's actually really growing very quickly. And I might add that it's probably also interesting to note that the most popular frequency band is the 3GPP's band 3, or the LTE 1800 band, which is in large part due to the refarming of the GSM bands.
Okay, good, thank you, interesting. One last question quickly here. I know you didn't discuss it here, but can you talk a little bit about the Zadoff-Chu sequences?
Okay. The Zadoff-Chu sequences actually have some useful properties as it relates to LTE. Namely, they have a low cross-correlation, they have zero autocorrelation, that is its orthogonality, and constant amplitude. And these sequences are used in a number of channels in the uplink and the downlink, most notably in the primary synchronization channel. And by using it with the E-node-B transmissions, it reduces the intercell interference, and it makes it easier for the UE to decode and get the cell ID. And in addition, the constant amplitude nature of the signal helps to reduce the cost and the complexity of the power amplifier designs.
Okay, great, thank you. And it looks like that's all the time we have for questions today. Thanks again for your presentation, Frank. And as we wrap up today's presentation, remember that we will email you a link when the on-demand version is ready to view, along with a copy of the slides. If you're currently viewing this on demand and have a question about any of the material, please do email Frank at the email you see on your screen now. I'd also like to remind our on-demand viewers to please complete the survey that will automatically launch at the end of the webcast. Thank you again for attending today's event, LTE and the Evolution to LTE Advanced Fundamentals webcast series brought to you by Agilent Technologies. Please visit us at agilent.com/find/events for more details on our future webcasts. There you can register for the second part of this LTE webcast series, which will take place on Thursday of this week. The copyright of the presentation materials is owned by Agilent Technologies.